Hi, this is a video for Unit 20, BTEC Applied Science, Medical Physics Techniques. I'm starting off with 20.1 and in this video I'll just look at P1, which is describe radioactivity including atomic structure. So let's get started with P1. Before I start, remember that on Moodle documents there is a list of references that you can use, and I've put page numbers for the two main books, which I'll show you in a moment, into groups for 20.1, 20.2 and so on. So by assignment you can get those references from that document. So look at that. It's the general references for Unit 20. The two textbooks are firstly the BTEC textbook. That has a section on Unit 20, so feel free to have a look at that. That will be useful information, particularly for the passes. And this textbook here, Medical Physics Imaging by Gene Pope, that's a really good textbook. This goes into a lot more detail than obviously the BTEC textbook can, because it's just covering the key areas that are required for the assignments in Unit 20. This one goes into a lot more detail. If you're attempting merits and distinctions, then you will need a copy of this book. You can get it in the library. So yeah, get one of those. And the relevant page numbers, they're on that list of references, so you don't have to look too far around the book to find what you need. Right, back to P1 then. Describing radioactivity, including the atomic structure. What I'm going to do is go over the content, and then I will go over how we apply that to the assignment that is required. So the first thing, what is radioactivity? Well, radioactivity is where you have a nucleus which is unstable. It wants to break down, and when it does so, it turns from something we call the parent nucleus, that's what you start off with, into a daughter nucleus. Okay? And it does that by ejecting either a particle or an electromagnetic wave, maybe even both, but we're just looking at the easier examples of one or the other, a particle or a wave. So you have your parent, and that turns into a daughter plus some particle or wave. Okay? Now the important thing here is that this is unstable and the daughter nucleus is more stable. So we go from an unstable nucleus to something that is more stable. So radioactivity is all about particles or atoms becoming more stable. Okay, so atoms become more stable during a radioactive decay. There are 4 types of radiation that you can have. 1, you can have alpha radiation. 2, beta minus. 3, beta plus. And 4, gamma. Okay, so those are the types of radiations or the types of decay that you can have. So let's have a look at those in general terms first. What is alpha decay or alpha radiation? Firstly, it is a particle. So it's a particle, and its nature is it's a helium nucleus. Excuse me. A helium nucleus. Okay, so helium atom, you have 2 protons, 2 neutrons, and 2 electrons. But this is just the nucleus, so it doesn't have the electrons. It's 2 protons and 2 neutrons only. It's very ionizing. So when we talk about ionizing, we're talking about the ability of this particle to turn atoms around it into ions. because it's this helium nucleus, it's got these 2 protons there. It's got a +2 positive charge in terms of the elementary charge. So it's got a lot of potential to draw electrons away from the surrounding atoms and therefore turn them into ions. It's got a lot of potential to do that, so it's very ionizing. However, it cannot travel very far, okay, so it has a very short range. Now let's put this into some practical context. Well, we're talking about 6 centimetres of air. So air is not made up of nothing, it's made up of lots of molecules that you can't see, but they're all there, and they will block the helium nucleus, the alpha particle, from travelling very fast, so about 6 centimetres. So I could have a source of alpha, if it's pure alpha, and I held it here, aimed at my hand, then the alpha particles, wouldn't be able to reach my hand, because the alpha particles will be stopped by the air molecules. And also, you would only need a very thin sheet of paper or foil to stop the radiation travelling very far, travelling through it. So if I had aluminium foil, the alpha particles would not be able to penetrate that, or if I had a thin sheet of paper, so you can use that to block alpha radiation. Okay, that's the key information that we need to know. But for all of the radiations, the way that we represent what's happening in terms of atomic structure is we would use decay equations. So X, that's our parent nucleus, Y is our daughter nucleus, and then that symbol there, that's an alpha symbol, it's a Greek letter, comes from the Greek alphabet, and that is the alpha particle. So in alpha decay, our parent nucleus turns into the daughter nucleus plus the alpha particle. Now, we need to have some numbers there to show what's happening with the number of protons and then the number of neutrons and protons. So what we would do is we'd have Z here for the proton number, A for the nucleon number. A nucleon is a proton or a neutron. Both are collectively called nucleons. So this has A and Z, and the alpha particle is 2 protons and 2 neutrons. So if you add 2 and 2, you get 4. So that's what we have for the alpha particle. Now, in order for this equation to be balanced, the number we must have here would be A minus the 4 from there. A minus 4. And the number down here for Y, the proton number here, be Z minus 2. So that's how you would work out what's going on with that equation. So that is the general equation for alpha. Let's give it, let's have a look at a real example of an alpha decay now. And the examples I use, they're not ones that you can use in your assignment, because obviously that would just be copying what I've done. But you're meant to use this general idea of the alpha, or this general representation of the alpha decay equation, and using your own isotope, work out what the numbers are for your daughter nucleus. So the example I'm going to use is uranium-235. It's 92. Okay, so uranium-235, and that's going to decay by alpha decay, and it will decay to something called thorium. Now, you won't need to know what each decays to in your cases, because I have a table which I'll show in a moment, and I tell you what it decays to if you need to know that. So yeah, our uranium decays to thorium. Remember that there's also the alpha particle to go in there. And we know an alpha particle always has 4 on the top, 2 on the bottom. So to work out what the mass and the nuclear mass number and the proton number are, we do 235 minus the 4, 231. So the numbers over this side must equal the numbers over this side. And 92 turns into 90 there, plus the 2 there. So that's quite similar to what you're probably used to from chemistry equations, balancing equations. That is our decay equation for uranium-235. That's alpha. Now we're on to beta minus. So let's write that over here. Okay. Beta minus is a particle again, but it's not a helium nucleus this time. This time it's an energetic electron, or a fast-moving electron. One of the misconceptions with beta minus is that the electron is one of the orbital electrons. That's not true. This electron comes from the nucleus. In our parent atom, it's the nucleus which is unstable. It's the nucleus which breaks down. So all of these radiations, they come from the nucleus, whether it's an alpha, a beta minus, beta plus, or the gamma. They all originate at the nucleus. So this, even though it's an electron, it's not coming from one of the orbital electrons, it is from the nucleus. This one has a low ionizing power. So it's significantly lower than the alpha radiation. So it's an electron, it has a negative charge, same as other electrons. It's going to have to get very close in order to exert much influence over them. So it doesn't have much, and it's very unlikely for that to happen, so it has a low ionizing power. It has a medium range as things go. Okay, so we're talking about here a few meters. A few meters in there, and here you can use a few millimeters of foil, of aluminium, sorry. A few millimeters of aluminium will stop beta particles, so that's the penetration power as well. The general decay equation for beta minus is, again using an X for our parent nucleus and a Y for our daughter nucleus. The beta equations students find a little more challenging because you have your beta, okay, so that's the beta there. But you also have something else, and it's an electron neutrino, but in our case it's an antineutrino. So this is a particle, you can have particles and antiparticles. Because this is a particle, the neutrino is an antineutrino, so it has a bar over the top. Okay, you don't need to know the reasons for that, but just appreciate that it's there. And in beta plus, you'll see there is an electron neutrino, but it's not the antineutrino, it's the particle version. They don't contribute any numbers for the nucleon or atomic number, so it's just 0, 0. So it's a pretty straightforward calculation like before. We have A there, Z there. This is -1. So it's an electron that's -1 and 0. It's not a proton or a neutron, so it's not a nucleon, so it has 0 at the top. So to work out what's changed, well, A has not changed because this value plus 0 must equal A, so therefore that's A. And then the Z, Well, this value minus that, minus 1 plus 0. So this is going to be z plus 1. So z plus 1 minus 1 will give us z. So that's how you balance that one out. A real example of this, we're going to use aluminium 34. I think it's 21. Oops, sorry. That's a bit high. Okay. 13. Okay, and that decays to silicon plus your beta. And again, just as over here, we knew that the alpha has 4 and 2. Alpha always has 4 and 2. It's only the daughter nucleus that you've got to do any calculations for. Here we know that the beta minus is minus 1 and 0 there. And the antineutrino is 0, 0. So let's balance these numbers. Well, this number doesn't change. The nucleon number is the same. This number needs to increase by 1 so that when we take 1 away, we end up with the same number. That is then 14. So if you look on a periodic table, we should find that silicon has an atomic number of 14. So we should only have done that correctly. That is beta minus. Let's have a look at beta plus. Let's get rid of this. Okay. As you can imagine, this is beta minus, this is beta plus, so they have an extremely similar nature. They are, in fact, this is the particle and this is the antiparticle version of it. So I'm going to just write down particle, and by that I mean it's a particle and not an electromagnetic wave. It is, however, an antiparticle. What it is this time is a fast-moving positron. So here it's an electron, here it's a positron. So positron is the name for the antiparticle of the electron. And then these two features or characteristics, the low ionizing power, the medium range in air, and a few millimeters of aluminium, those are the same as over here. Beta minus. So the same as beta minus for the ionizing and its range. The general equation is slightly different, has a very similar format. Here it's plus 1 and 0, and this doesn't have the bar over the top. It's just like that. So the bar indicating that it was the anti-neutrino, this is the neutrino. We have A, we have Z. So A doesn't change, but the Z number for this, for Y, is going to be Z minus 1. So when we do Z minus 1 plus 1, we end up with Z again. So that's the general equation. Let's take another isotope of aluminium, aluminium 22. So the proton numbers are the same, so that we're dealing with the same element. That decays to, this time it decays to magnesium. This number, same, 22, and 13 minus 1 is 12, so 12 plus 1 gives us 13. So the equation is balanced, and that's what you get. So again, magnesium on the periodic table, you can see that it has an atomic number of 12. So that's 3 of our radiations. Done alpha, beta minus, beta plus. The last one is gamma, and gamma is dead easy in terms when it comes to doing an equation. That is. Right. Gamma. So this one is the only one that is not a particle like the others. This one is an electromagnetic wave. You can call it a photon if you like, which is actually, we're going into quantum mechanics here. Electromagnetic radiation can behave like a particle or a wave, and so what's emitted is actually a gamma photon. But you can, for our purposes here, just call it an electromagnetic wave or a photon if you like. So it's an electromagnetic wave, it's a gamma photon, that is its nature, and we need to look at the ionizing power. This is very weak. Okay. This is unlikely to interact with any electrons, so it's very unlikely to remove any electrons from atoms or molecules. It has to interact directly with an electron, and what it would do is it give the electron energy to escape the atom, leaving behind an ion. The range is obeys an inverse square law of distance. So if you double the distance, then the intensity of the radiation being emitted from your unstable nucleus will fall to a quarter of the initial value. So basically, the further away you get, the weaker the radiation is. Not as much radiation is reaching that range. To penetrate the penetration power, you're going to need thick lead to stop it. So if you have a source that is emitting gamma radiation, you'll need to put that in some container with a lot of lead surrounding it to keep the radiation from escaping that container. The general equation, there's our gamma radiation there. That has 0 and 0, so it's not a nucleon and it doesn't have an atomic number. So the gamma photon, that has 0, 0. Now, essentially what happens in this radiation is, whereas the others, they were unstable because they had too many protons and neutrons. That's the cause for alpha decay. When it has too many protons and neutrons, it needs to lose some of those to become more stable. So it's essentially just losing mass. It ejects that mass from the nucleus. The beta minus and beta plus, they happen because the nucleus has too many neutrons compared to protons, or too many protons compared to neutrons. So it either needs to lose a neutron and gain a proton, or lose a proton and gain a neutron, depending on which type of instability it has. And that, by doing that, it becomes more stable. So these radiations previously were losing some particles or gaining particles to become more stable. Here, what's happened is the nucleus has too much energy, and so it needs to lose energy, pure and simple. So gamma radiation, it emits the gamma radiation, and the gamma photon carries the energy away from the nucleus. So that's how that's why it occurs. To indicate that, what we do is use an M. That M after the A indicates that it has too much energy. So essentially that M becomes the gamma photon, and then all you have to do is write in the A and the Z numbers there. So it's pretty straightforward. Sometimes you may see an asterisk by the symbol. That also can be used instead of the M to indicate that this nucleus, or the nucleus of this atom here has too much energy, so it needs to lose it in the form of a gamma photon. Whichever one you want to use, just be consistent with it. So let's have a look at an example. I'm going to use krypton here, which is 8636. So 86M, the M indicating it's got too much energy, and that decays into krypton. There we go, and that is the decay equation for the gamma. So that is the general theory that we need to cover. Let me now go through how you need to apply this to your assignment. First thing, you need to describe what radioactive decay is in general terms. So that's talking about this unstable nucleus. It needs to turn into the daughter nucleus, which is more stable by emitting a particle or wave. So just a very brief discussion or description about that. You need to describe what the nature is of each of the radiations. So are they a particle, are they a wave, what type of particle, what type of wave are they? You then need to talk about you need to give the equation for each one. So the equation, you can state this general equation if you like, so that's just copying that straight out. But the one that you will be marked on is your application of the general equation to a real isotope. So I've used these isotopes, you can't reuse those. To find out which isotopes you can choose from, you use the table which is on the back of the assignment brief. And on there I have a number of isotopes. There are 2 that decay by alpha, 2 by beta minus and 2 by beta plus, and 2 by gamma. You choose one for each, so you don't do all of them. Let's say you're doing alpha, and I've got polonium 212 and radon 220. So either do polonium 212 or radon 220. So I've indicated which type of decay they decay by. I've also told you what they decay into. So I've only told you the element. I haven't given you the A and the Z numbers. You need to work that out. For P1, that's all you need to worry about. Those first 3 columns. The half-life of the decay constant, that's for the merit task. So you've chosen which one you're going to do. You know it decays into polonium or lead, and so what you do is you write your decay equation with those symbols and work out the numbers that you should have, knowing that the radioactive particles or waves, they always have the same numbers as I've shown you in these equations. If you're doing, well, you're going to have to do one of the gammas. So there's 2 options here, the cobalt 60 and the technetium 99M. Well, for both of those, you'll notice that I didn't tell you what they decay into, because that should be obvious. So remember what I was discussing as I was looking at this equation here. Right, last thing you need to do is describe the changes that occur in the atomic structure. So, does the parent nucleus lose some protons and neutrons? If so, how many does it lose? Does the nucleus lose 1 neutron and gain something else, or does it lose a proton and gain something else? So discuss what that is. You should be able to work out what's happening from the equation. So in this one, for example, we can see that the proton number has reduced, so it must have lost a proton. But the nucleon number stayed the same. So if you ordinarily, if you lose a proton and nothing else happens, then that number will decrease by 1. So we know we've lost a proton, but we've also gained the other type of nucleon that you can have. So lost that, gained the other nucleon, whichever that may be. Over here, both numbers are identical. So was there a change to the number of protons and neutrons in that nucleus. You can work it out from the numbers.